Hello, everyone. Welcome back to AIQuantEasy from zero to hero. In the previous episodes, we discussed how to train supervised learning models to make certain prediction on stock market. Starting from this episode, we will use a different machine learning technique that is called reinforcement learning to learn optimal trading strategies. Unlike supervised learning, which is trained to make certain predictions, reinforcement learning will not make predictions. Instead, it will learn optimal actions to take in different situations of the environment through trial and error. Reinforcement learning, just like supervised learning, is a category of machine learning techniques. So in this category, we have different machine learning algorithms. The one that we will use in this episode is called deep Q-learning. In this episode, we'll first talk about how we model stock trading by using reinforcement learning. Then in the next episode, we will discuss how to implement deep Q-learning for optimal stock trading. Let's first talk about the basic concept of reinforcement learning. For any reinforcement learning systems, there are two big components. One is called environment. The other is called agent. So agent interacts with the environment. Given a time point, the agent observes the current state of the environment. Then, based on this state, the agent make a decision according to the policy of this agent by choosing the action to take on this environment. So this action will cause some effect on this environment by shifting the state of the environment from the current state to the next state. The effect on the environment by this action will bring this agent a reward. We call it reward, but this reward value could be positive or negative. It's negative. Actually, it's a penalty, right? So anyway, so the agent choose an action to take according to the agent's policy based on the observed current state. And this action will have the effect on this environment by bringing the state of the environment to the next state. And this effect will bring this agent a reward. Okay? Then this process will continue, right? So the agent observe the new state of the environment. And based on this new state, then the agent will choose action to take according to its policy. This action will have an effect on the environment by shifting the state from the current state to a new state. Again, this effect brings the agent a reward. Then the agent continue to choose the action to take based on the new state. And this action has effect on the environment by shifting the environment from the current state to a new state and continue this process until what? Until it reaches the last state. Then we call the whole process an episode. Once an episode is completed, the agent can choose another state to begin with another episode. Okay, so basically every episode provides data to train this agent such that it can take better and better decisions by choosing more optimal actions for a given state. So that is the overall high-level description of how reinforcement learning works. The high-level description of reinforcement learning process may still sound very abstract. So now let's just put this process in the perspective of stock trading so that you may gain more solid understanding of it. So remember that we have a data frame that stores SPY daily price and volume data, right? And also we derive a bunch of indicators, right? So the attributes that we have for that data frame looks like this: open, high, low, close, volume, and some indicators, right? So these are the attributes that we have for that data frame. These attributes plus our account setting, including current cash value, current number of shares, all these can be used to define our environment. Okay, so in other words, our environment includes all these attributes and our account setting, the cash value, and the number of shares. Given a day, and at the close of that day, right? So we have particular values for all these attributes. And also for that day, we have the current cash value and the current number of shares. So all these concrete values for that given day form a state of the environment. So every day at its close, we have a state. Different days, we have different states, right? Different states means that we have different values for all these attributes. We have different values for cash value and different values for number of shares, right? So given a day at its close, we have a state for this environment. The agent observes this state, then according to its policy, it will take action. So here we assume that the action that an agent can take is one of these three: buy, sell, hold. If the action is buy, then we will buy one share of SPY and close of that day. If the action is sell, then we will sell one share of SPY at its close. If the action is hold, that means we don't buy, don't sell. Okay, we don't do transaction. Okay, one of the actions that the agent will take based on the current state, based on the state, the values of these attributes and the values of the account, right? And the action take on the environment will bring an effect on the environment, right? So let's see, if the action is buy a share, okay? So if it's buy a share, that means what? That means we will use some cash to purchase a share. So our number of shares will increase and the amount of cash value will decrease, right? And also we will look at the next day's close. And as the next day's close, all these values may change, right? May be changed. So for the next day at the close, we have new values for all these, and we have new cash value and new shares. This new cash value, new shares, number of shares are caused by the action that the agent takes: buy, sell, or hold, right? So this action will have an effect on the environment by moving the state of the environment from the current day to next day. And also, this change on the environment will bring a reward to the agent. So here, the reward will be calculated by the total account value, including the cash value plus the number of shares times the close price of SPY at the next day. So we can calculate the total account values of next day after the action is taken and the total cash value of the current day at the close before the action is taken. And the difference between the account values, at the close of next day and at the close of the today, that reflects the value change caused by the action that is taken by the agent, right? So that is our reward we give to agent. Again, this reward could be positive or negative, right? So in other words, your account value may increase due to your action or maybe decrease due to your action, okay? Then once we have a new state here, the agent observe it, then according to its policy, it will take action. Again, action is one of these three, right? Buy, sell, or hold. This action will have an effect on the environment by bringing the state of the environment to the new state. And that effect on the environment will bring the agent a reward, a count change, count value change, right? And then we continue this process. Basically, the agent observes a new state. Then, according to its policy, it will choose one action to take on the environment, then bring the environment to a new state, and then continue this process, right? Until the agent reaches the last state. Then that's called an episode. Then the agent can choose any day to start with, right? And then starting a new episode. So agent can goes through many episodes, 1,000 episodes, 10,000 episodes, and so on, right? So all these episodes actually brings data to train the agent, okay? So such that the agent will learn from the past experiences to the extent that given a state, the agent will make more and more profitable decisions, through the learning. So in other words, given a state, the agent becomes smarter and smarter by choosing the actions that can bring the agent more profit. Okay, so that's another description of the reinforcement learning process. I put it in a perspective of SPY daily trading. After we have a better understanding of the process of reinforcement learning, let's just talk about the deep Q learning. As I mentioned earlier, deep Q learning is a popular model under the umbrella of reinforcement learning. How deep Q learning works? Basically, deep Q learning uses a deep neural network that we call it Q network to implement the policy. Recall that agent has a policy that determines what action to take given the current state, right? So deep Q learning use this deep Q network to determine which action to take based on the current state. In other words, deep Q learning use this Q network to implement the policy or express a policy. The current state that is agent observed is used as an input to this deep Q network. Then this deep Q network will output a Q value for each of the actions. So here we have three actions for the stock daily trading case: buy, sell, and hold. So we should have three output neurons. So in this diagram, we show four, but for this case, we need to have three output neurons. The first one represents buy action, the second output represents sell action, and the third represents hold action. Okay, this deep Q network will output a value for each action based on the current state. Like the value that is the output for buy action is called Q value for buy action. The Q represents a quality. So Q value represents a quality value for buy action. So this output neuron will have a Q value for sell action, and this will have a Q value for hold action. Okay, Q represent quality. Again, quality value. So if an action has higher quality, that means this Q network think that action should have higher probability to be taken by the agent. Okay, so that means that is an action that may bring more reward towards the agent after that action is taken. Initially, this Q network starts with randomized parameters. In other words, all the weights along these edges are randomized. So that means the initial output of the Q value for each action is not meaningful. They're just random values, right? But through the process that the agent interacted with the environment, like we mentioned through all these episodes, right? We accumulate a lot of data of how the agent interact with the environment. And through those historical data, we can train this deep Q network to optimize the parameters such that the Q value output for each action will be more and more meaningful instead of initially just random values. So the Q values outputted by the network based on the current states become more and more meaningful. That means the actions that the agent is taking according to the output Q values will be more and more profitable. Okay, so that means those actions will bring more and more reward to the agent. Okay, so again, the agent interact with the environment through many episodes, 1,000 episodes or 10,000 episodes. And those episodes bring a lot of training data for us to train the agent. Train the agent means to train this deep Q network. And that means we optimize all the parameters of this network such that the output, the Q values for each action will be more and more meaningful. And those actions that have higher Q values, they will have a better opportunity to be taken under the current state, right? And those actions should be the one that those actions that have higher probability to be taken should be the one after training, the one that have the higher opportunity to bring more reward to the agent. Okay, so that is the simple description of the deep Q learning. So they use a deep Q network to implement the policy. Okay, so you can imagine that this network itself represents the policy, right? They take the state, the current state as an input, the output, the quality value, Q value for each action. Then the agent will have a higher probability to take the action that has higher Q value. Okay, so that's basically the deep Q learning. Now we will take a closer look how the data that we accumulated through many episodes of agent interact with the environment can be used to train this deep Q network. Now let's zoom into the procedure where the data accumulated for each episode is used to train this deep Q network. Recall that for each episode, we record each interaction between agent and the environment into a memory, which is called a replay memory, right? For example, when the agent observes the current state, S1, then the S1 will be used as an input to this deep Q network, and it will output the Q value for each action, right? And the action with higher Q value may have better opportunity to be taken on this environment. So once that action is taken on this environment, it brings a direct reward, R1, okay? And also it will cause the environment shifting from state S1 to a new state S2, right? So basically, that's one interaction. We record the following information for this interaction, the state S1 and the action that is chosen for state S1, that's A1. And the A1 is taken on this environment, bring R1. And A1 will shift the environment from S1 to S2, right? So basically, we will record S1, A1, R1, and S2, right, as the information for this interaction. Then we start with S2, beginning another interaction. We will record the same information. So through the episode, the information that we will record in the replay memory looks like this, right? Looks like this. So everyone is a tuple of four values, S1, A1, R1, S2. Then start with S2, take action A2, bring the reward R2, then change the environment from S2 to S3, and so on. Okay, so this is one episode. We store the information in the replay memory. So once we have this episode completed, then we will use this stored information to train the Q network to optimize its parameters such that the output Q value will be more and more meaningful, right? So that's our goal. Again, once we use the data for this episode to train the Q network, then we will go to another episode, record all this information for another episode as well. Then again, use those data to train the Q network again and again through many episodes, right? So let's just focus on one episode right now. So assume that we already record all the interactions between the agent and the environment for this episode in the replay memory. Okay, now let's see how we use this data to train the Q network. Okay, so each time for training, we will take a mini batch from this replay memory. So in other words, we'll randomly pick a certain number of records from this replay memory to train to train the Q network. Okay, assume that our batch size is 64. So every time we will randomly pick 64 records from the replay memories to train the Q network. Okay, in order to train the Q network, so this is Q network, right? So the output string values, each one is a Q value for each of the three actions, right? Okay, so in order to train this neural network, in other words, in order to optimize the parameters, the theta, all these parameters, we duplicate this neural network into two portions. One is called prediction neural network. Another one is called a target network. So initially, they're identical, right? So prediction network is used to output the Q value for each action based on the observed state, right? So that's basically how the agent pick the action to take. Then the target network is used to calculate the target Q value that we want this network to output based on S, a state S. Okay, what does that mean? So that means you see, given the state S, this network outputs a Q value for each action, right? So most likely, the action with the higher Q value will be chosen by the agent to take on this environment, right? So this action that is chosen by agent on this environment will directly bring the reward. That's R1, right? That's R, reward. Will directly bring the reward, right? But also this action will bring the environment from the current state S to a new state, which is S prime. So once the environment gets into S prime, again, on S prime, basically, you may have profit may get, right? So in other words, on S prime, you can take one of the actions as well, right? So basically, if each of these actions may have a reward as well. So basically, we input S prime into this target network. Initially, again, it's identical with this prediction network. So we use S prime, which is a state caused by the action A1 as an input into the target network. So it will output the Q value of each action based on S prime. So S prime is a state that directly caused by action A1. So action A1 directly bring a reward R1, but also cause S prime, right? S prime, based on S prime, then we may further get profit, right? Get a reward. So we will choose the action with the largest Q value as the estimated reward that can bring based on S prime. So we will use this maximum potential reward that can be brought on based on S prime as partially the desired Q value for action A1. The reason for that is that S prime is directly caused by A1 on the environment, right? A1 caused the environment shifting from S to S prime. Okay, so basically, again, the desired Q value for action A1 will be calculated based on R, the reward directly brought by A1, and the maximum Q value based on state S prime, because S prime, again, is the direct effect as well of A1 on the environment, right? So on this state S prime, basically there's a potential reward as well, but this state, since it's directly caused by action A1, so we will partially count it as the reward that will be brought on S prime as kind of like a desired reward for A1 as well. So the desired target Q value of A1 is calculated by R plus the maximum quality value of S prime. Okay, so the maximum quality value of S prime is calculated by inputting S1 into this target network. Then we choose the action with highest quality, right? Quality value, and that quality value will be used to added to the reward get by action A1 to be the final target reward or target quality value of action A1. Okay, so basically on the one hand, we have this target quality value for action A1. On the other hand, we have the target that we have the real quality value output by the prediction network. So they have differences. So that differences is the loss. Basically, we want to minimize for this prediction network. So basically how the network can be trained or how the parameters of this network can be optimized. The parameters of this network will be optimized by minimize the loss, right? So for each tuple, basically, in a mini batch, we calculate such a loss, right? For 64 tuple, we have 64 such a loss, right? So within this mini batch, we use this loss to basically modify the parameters of this network. How to modify? We use gradient descent techniques to modify the parameters in order to minimize all those loss values. Okay, so in this way, basically, we can optimize gradually all these parameters of this secure network. So after maybe a bunch of mini batches, right, we copy the parameters learned for the prediction network to the target network as well to keep the target network updated with the prediction network. So the prediction network will be updated for each mini batch, right? After C mini batches, so we will copy the parameters learned by these prediction networks through those mini batches to the target network, such that the target network will keep the same parameters as a prediction network. Again, target network will take the new state S prime as an input, then output the Q values for each action based on S prime. Okay, so that will become partially counted as the potential reward that can be obtained by action A1. Okay, again, A1, the potential reward of A1 contains two parts. The first part is the direct reward caused by A1. The other part is because A1 make the state of the environment change from S to S prime, and on S prime you have the other potential to get a reward, right? So that reward again partially contribute to the potential reward caused by R1, caused by A1, action A1. Okay, so that's our target reward value. And the target reward value minus the current Q quality value output by this prediction network for based on S1, based on the state S, we have the loss. The difference is a loss. Okay, we want to minimize the loss by optimizing this parameter using gradient descent, right? So again, we get multiple mini batches from this episode, right? And for each mini batch, we modify this. After several mini batches, we copy what we learned from here to the target network. Okay, then we get another mini batch, continue this process, right? So after we finish with this episode, then we go through another episode and record all the records for that episode, then starting this learning process as again, right? So hopefully through all these trainings, so the parameters will be optimized for the prediction network, and the output, which is the Q value for each action, will be more and more meaningful, more close to the reward value that the real reward that the action can be, the potential reward that each action can bring, right? So this is a rough description of how this Q network is trained by using each of those episodes, you know. So in the next episode, we'll talk about the implementation by using Python. Stay tuned.